Welcome to Backend Development, a Practical Guide. This audiobook is for curious minds, aspiring developers, and anyone interested in understanding how modern applications work behind the scenes. While the front end is what users see, the backend is the invisible engine that powers everything, from handling data to ensuring security, scalability, and speed. In the following chapters, we'll explore the key building blocks of backend systems. You'll learn about APIs, databases, authentication, event-driven architecture, cloud deployment, and more, all explained in simple terms with real-world relevance. Whether you're just starting your tech journey or brushing up your backend knowledge, this guide is designed to be clear, beginner-friendly, and grounded in practical thinking. There's no need to have deep programming experience, just a willingness to learn how systems talk, store, and scale. Let's begin our journey into the world of backend development. Welcome to Chapter 1, One Concept. In this first chapter, we'll explore a foundational question: what exactly makes a good backend? The backend is the unseen part of an application, the logic and infrastructure that power everything users see and do on the front end. It's responsible for handling data, responding to user requests, securing information, and coordinating the core business logic. But what makes a backend good? First and foremost, it needs to be reliable. That means it should handle requests consistently, without crashing or producing unexpected errors. It should also be scalable, able to grow as more users or data come into the system. Whether it's 100 users or a million, a good backend should perform smoothly. Security is another critical factor. A backend must protect sensitive data, validate input, and guard against attacks. Features like authentication, encryption, and secure communication all play a part in making the system trustworthy. Maintainability also matters. Clean, well-structured code makes it easier for teams to add features, fix bugs, and adapt to changing needs over time. Using standard patterns, modular architecture, and clear documentation all help here. Then there's performance. A good backend responds quickly, manages resources efficiently, and minimizes bottlenecks, whether it's a database query or an API response. In terms of technology, backends are typically built with languages like JavaScript, Python, Java, Go, or Ruby, often paired with frameworks such as Express.js, Django, Spring Boot, or FastAPI. Each offers different strengths, but all aim to make development more productive and systems more efficient. Ultimately, a good backend is more than just functional code. It's a thoughtful system designed to serve users reliably, securely, and efficiently. In the next chapter, we'll dive into one of the core tools of backend development, APIs, the connectors that allow understanding APIs, the language of systems. In this chapter, we explore one of the most essential parts of backend development, the API, or Application Programming Interface. At its core, an API is how different software components communicate. Whether it's your mobile app requesting new content, or a weather widget displaying current temperatures, an API sits in the middle, receiving a request, processing it, and delivering a response. In backend development, APIs act as the bridge between the client, such as a front-end interface, and the backend logic. They define what a client can ask for, how to ask for it, and what format the response will be in. Most APIs today follow the REST architectural style, short for representational state transfer. RESTful APIs use standard HTTP methods: GET to fetch data, POST to create something new, PUT to update existing information, and delete to remove it. For example, a get/users endpoint might return a list of users, while a post/users call could create a new one. These endpoints typically return data in a standard format, like JSON, making them easy for other systems to read and use. A well-designed API is intuitive, consistent, and secure. It should validate requests, return clear error messages, and avoid exposing internal logic or sensitive data. That's why authentication methods like API keys, OAuth tokens, and JWTs are commonly used to protect endpoints. Tools like Postman, Swagger help developers design, test, and document their APIs efficiently. They make it easier to share how your system works with other developers, whether internally within a team or externally through public APIs. How applications handle data. In this chapter, we'll explore databases, a cornerstone of backend development. Simply put, a database is where applications store, organize, and retrieve data. Whenever you log into a website, post a message, or browse products, data is being saved and fetched from a database behind the scenes. There are two main types of databases commonly used in backend development: SQL, relational, and NoSQL, non-relational. SQL databases store data in tables with rows and columns much like a spreadsheet. They use a structured query language called SQL to manage and retrieve data. Popular examples include MySQL, PostgreSQL, and Microsoft SQL Server. SQL databases enforce schemas, which means the structure of the data, like what columns exist and what types of data they hold, is defined ahead of time. This helps keep data consistent and reliable, especially for complex transactions. On the other hand, NoSQL databases offer more flexibility. They store data in formats like documents, key value pairs, or graphs. This makes them ideal for handling large volumes of unstructured or semi-structured data. Examples include MongoDB, Cassandra, and Redis. NoSQL databases typically don't require a fixed schema, allowing developers to iterate and evolve the data model quickly. They often excel at horizontal scaling, spreading data across multiple servers for performance and reliability. Choosing between SQL and NoSQL depends on your application's needs, whether you prioritize strong consistency and complex queries, or flexibility and scalability. Beyond storage, backend developers also focus on how to efficiently query and index data to speed up responses, ensure data integrity, and handle backup and recovery. In the next chapter, we'll discuss authentication and security, vital topics to keep data and users safe in any backend system. Understanding databases is fundamental. They are the foundation that supports every user action and feature in modern applications. Authentication and security. Protecting users and data. In this chapter, we focus on one of the most critical aspects of backend development: authentication and security. Without them, even the most powerful application is vulnerable. Authentication is the process of verifying a user's identity. It answers the question, who the user is. Common methods include usernames and passwords, one-time codes, biometric checks, or external identity providers like Google and Facebook through OAuth. Authorization, which often follows authentication, answers what the user is allowed to do. Even after logging in, users may only have access to certain data or actions, depending on their role or permissions. A widely used method for secure authentication is JWT, JSON Web Tokens. After logging in, the server sends the client a token that is used for subsequent requests. This avoids storing sensitive session data on the server while maintaining security. Beyond authentication, backend developers must guard against common security threats. SQL injection, for example, occurs when malicious queries are inserted into input fields. Cross-site scripting, XSS, allows attackers to inject harmful scripts into web pages. To mitigate these risks, it's essential to validate inputs, escape outputs, and follow secure coding practices. Encryption is another key layer of application security. HTTPS ensures that data transmitted between client and server is encrypted, preventing eavesdropping. For stored data, encryption at rest ensures that even if a database is compromised, the data remains unreadable without the correct keys. Implementing rate limiting and IP blocking can help defend against brute force attacks and denial of service attempts. Meanwhile, using security tools like OWASP ZAP or following guidelines from the OWASP Top 10 helps keep vulnerabilities in check. Security is not a one-time task. It's an ongoing process of monitoring, updating, and adapting to new vulnerabilities. In the next chapter, we'll explore event-driven architecture, a design approach where systems react to events in real time, creating more responsive and scalable applications. Remember, the trust of your users depends on how seriously you take authentication and security. In backend development, protecting data is just as important as providing event-driven architecture, building reactive and scalable systems. In this chapter, we'll explore event-driven architecture, a design pattern where systems respond to events as they happen. Instead of a constant back and forth between client and server, components react to specific triggers, making applications more efficient and scalable. An event is any significant change in a system, a new user registration, a completed payment, or a sensor sending data. In an event-driven setup, these events are captured, processed, and used to trigger actions elsewhere in the system. At the heart of event-driven architecture is the publisher-subscriber model. The publisher generates events and sends them to an event broker, a message hub like Apache Kafka, AWS Event Bridge, or RabbitMQ. The subscribers, or consumers, listen for specific event types and act when they receive them. This decouples components so they can operate independently. For example, in an e-commerce application, when an order is placed, the order service might publish an order-created event. This event can trigger multiple independent actions. The inventory service updates stock, the billing service processes payment, and the notification service sends a confirmation email, all without direct calls between services. Event-driven systems excel in scenarios where scalability and responsiveness are key. They handle spikes in activity gracefully by queuing events and processing them asynchronously. This is particularly valuable in IoT systems, financial applications, and large-scale web platforms. Technically, event-driven systems can be implemented using event streams, message queues, or even serverless platforms like AWS Lambda, which execute functions in response to specific triggers. However, this architecture comes with challenges, ensuring event delivery guarantees at least once, exactly once, managing event ordering, and designing idempotent consumers, so repeated events don't cause unintended effects. Monitoring and debugging distributed events also requires specialized tools. In summary, event-driven architecture promotes loose coupling, high scalability, and real-time responsiveness, but requires careful planning in design and observability. In the next chapter, we'll look at scalability and performance optimization, where we discuss strategies to ensure backend systems handle scalability and performance optimization, keeping systems fast and reliable. In this chapter, we'll explore scalability and performance optimization, two key aspects of backend development that determine how well your application grows and responds under load. Scalability is the ability of a system to handle increasing amounts of work without degrading performance. There are two main approaches: vertical scaling and horizontal scaling. Vertical scaling means upgrading your existing server's hardware, adding more CPU, RAM, or storage. Horizontal scaling involves adding more servers or instances to share the workload, often managed by load balancers and orchestration tools like Kubernetes. While scaling addresses capacity, performance optimization ensures the system responds quickly and efficiently. This involves reducing latency, improving throughput, and minimizing resource consumption. Common techniques include caching frequently accessed data with tools like Redis or Memcached, database indexing to speed up queries, content delivery networks, CDNs, to serve static files closer to users, asynchronous processing to handle time-consuming tasks outside the main request flow. Another important aspect is monitoring and observability. Tools like Prometheus, Grafana, or AWS CloudWatch help track performance metrics, detect bottlenecks, and identify when scaling is needed. Scalability also requires thinking about fault tolerance and high availability. Systems should be designed to continue operating even when parts fail, using redundancy, failover mechanisms, and distributed deployments across multiple regions. On the development side, optimizing application code, reducing unnecessary computations, and following efficient algorithm design all contribute to performance gains. In microservices architectures, minimizing network calls and batching requests can also improve efficiency. In short, scalability ensures your system can grow, and performance optimization ensures it remains fast. Together, they create a backend capable of supporting millions of users without slowing down. In the next chapter, we'll discuss logging and monitoring, which help keep track of your system's health and behavior. Logging and monitoring, seeing inside your backend. Every well-built backend needs eyes and ears. That's what logging and monitoring provide, the ability to see what's happening inside your system, even when things go wrong. Logging is the process of recording events that happen during application execution. Logs can capture errors, warnings, debug messages, and important application milestones. They help developers understand the flow of the system and pinpoint issues when something doesn't work as expected. Common practices include using structured logging formats like JSON, adding meaningful log levels, and centralizing logs with tools like the ELK stack, Elasticsearch, Logstash, and Kibana, or cloud services like AWS CloudWatch logs. While logs are like a detailed diary, monitoring is more like a health check dashboard. Monitoring systems continuously track performance metrics such as CPU usage, memory consumption, response times, and request rates. This data helps detect problems before they impact users. Popular monitoring tools include Prometheus with Grafana for visualization, Datadog for a managed solution, and AWS CloudWatch metrics for cloud-native setups. A more advanced approach is observability, which combines logging, metrics, and tracing to give a complete picture of how requests flow through your system. Distributed tracing tools like Jaeger or OpenTelemetry help track requests across microservices, revealing where bottlenecks occur. Effective logging and monitoring aren't just technical niceties. They are essential for incident response. When an outage happens, well-structured logs and accurate monitoring data mean the difference between minutes and hours of downtime. In practice, a good backend system will set up alerts, define thresholds for unusual activity, and ensure logs are retained for the right amount of time for debugging and compliance. In short, logging tells you what happened, monitoring tells you how the system is performing, and observability helps you understand why. Together, they form the backbone of reliable backend operations. In our next chapter, we'll move to testing and quality assurance, ensuring that what you build is not only functional, but also robust and reliable before testing and quality assurance, building with confidence. In backend development, writing code is only half the job. The other half is making sure that code works as intended, not just today, but tomorrow, and under every possible condition. That's where testing and quality assurance, or QA, come in. Testing is the process of verifying that your application behaves correctly. It comes in many forms. Unit testing checks individual components or functions in isolation. ensuring small building blocks work as expected. Integration testing ensures different parts of your system, like the API and database, work correctly together. End-to-end testing simulates real user interactions, verifying that the whole application works from start to finish. Backend developers often use frameworks like Junit for Java, PyTest for Python, or Jest for Node.js. Automated test suites are essential because they allow you to rerun tests quickly whenever you change the code. This practice is called regression testing, and it ensures new features don't accidentally break existing functionality. Quality assurance goes beyond testing. It's about making sure the system meets requirements, handles edge cases, and performs reliably under expected loads. Techniques like load testing and stress testing simulate heavy traffic to ensure your backend can handle peak demand. Tools like JMeter, Locust, and K6 are popular for this purpose. A key principle in QA is shift-left testing, which means testing as early as possible in the development cycle to catch issues before they become expensive to fix. Modern DevOps pipelines often integrate continuous integration tools like Jenkins, GitHub Actions, or GitLab CI to automatically run tests on every code commit. Ultimately, the goal of testing and QA is confidence. Confidence that your backend is stable, secure, and ready for production. Without it, deployments become risky and debugging becomes chaotic. With it, you can move fast without breaking things. In the next chapter, we'll explore deployment strategies where we take your thoroughly tested backend and release it to the real world with minimal risk deployment strategies, and maximum efficiency. Releasing with confidence. Deploying a backend application is more than just copying files to a server. It's about releasing updates safely, minimizing downtime, and ensuring a smooth experience for your users. That's why choosing the right deployment strategy is critical. One of the simplest methods is the rolling deployment, where new versions of the application replace the old ones gradually, one server at a time. This ensures that part of the system is always running and reduces the impact of potential issues. Blue-green deployments take a different approach by running two identical environments. The blue environment hosts the current version, while the green environment hosts the new one. Once the green environment is tested and ready, traffic is switched instantly. This allows for near zero downtime and easy rollback if something goes wrong. Canary releases push updates to a small percentage of users first. If everything runs smoothly, the release expands to more users. This is a great way to catch unexpected issues in real-world conditions without affecting everyone. For backend systems in the cloud, serverless deployments like AWS Lambda or Azure Functions allow you to release updates without managing infrastructure at all. Containerized deployments with Docker and orchestration platforms like Kubernetes offer scalability, portability, and automation, making them a favorite for modern microservices architectures. Deployment strategies also tie into continuous delivery and continuous deployment pipelines, where tools like Jenkins, GitHub Actions, and AWS Code Pipeline automate testing, building, and releasing your application. Automation not only speeds up deployment, but also reduces human error. Regardless of the method, every deployment strategy should include rollback plans, monitoring after release, and gradual rollouts to ensure issues are caught early. In our next chapter, we'll cover maintenance and continuous improvement, where we discuss how to keep your backend healthy, secure, and evolving long maintenance and continuous improvement. Keeping your backend healthy. Launching your backend application is a major milestone, but it's not the finish line. The real work begins with maintenance and continuous improvement, ensuring your system stays secure, reliable, and efficient over time. Maintenance starts with monitoring your application's health through logs, metrics, and alerts. Tools like Prometheus, Grafana, and AWS CloudWatch can track performance, detect errors, and alert you to potential problems before they affect users. Security patches, dependency updates, and database optimization should be part of your regular maintenance cycle to reduce vulnerabilities and improve efficiency. Continuous improvement is about making your backend better with each iteration. This involves analyzing performance bottlenecks, refactoring code for readability and maintainability, and introducing automation to repetitive tasks. Conducting regular code reviews and postmortems after incidents helps uncover lessons that can prevent future issues. A strong maintenance process includes scaling strategies to handle growth, such as optimizing queries, adding caching layers, or implementing auto-scaling infrastructure. It also means staying current with technology trends and updating your architecture when it brings measurable benefits. In the world of backend systems, nothing stays static. Requirements evolve, user expectations rise, and threats emerge. The best teams treat their backend like a living system, one that's continuously observed, improved, and adapted. With consistent maintenance and a culture of improvement, your backend won't just survive in production, it will thrive. This brings us to the end of our journey through backend development essentials. From APIs to security, scalability to deployment, we've explored the core principles that power robust backend systems. The next step is yours, to take these concepts and bring them to life in your own projects.